Okay, good. So the condensate blockage kind of history, I'm going to try to go through that in brief. I think will help a little bit in understanding the details of what we talk about, this region 1 behavior, region 2, and so forth. That's part of the history. But we'll what I'm going to do is I'm going to start with there's actually in the book by Muscat, the second book by Muscat. He has a short section on gas condensate blockage, in fact, and he gives an approximate way to estimate the what I'm going to call the radius of blockage and the magnitude of gas permeability within that radius of blockage for a vertical unstimulated well. Now, this is generally not been used or adapted, as far as I'm aware of, in any software. And it doesn't treat some of the issues that are important, but it does give an approach to looking at the blockage. So that's from 1940s something. And then in another paper by Evinger and Muscat, what they do is that they treat the inflow performance relation, or the reservoir rate equation of solution gas drive reservoirs. Or wells producing in a solution gas drive reservoir. And that was 1940, I don't know when that was, 40 something. And I think it's in the notes. You can go look at it. It's pretty sure it's in the notes somewhere here. Just search for Evinger. Yeah. So it's 1941. And so, basically this is for when reservoir pressure and flowing bottom hole pressure drop below the bubble point. Okay. And they end up with the same equation that we talked about yesterday, introducing this concept of the oil mobility variation with pressure, same C, KH, log RERW, scan, and so forth. And the oil mobility they gave a procedure to calculate, let's see, above the bubble point. Of course, that's trivial. This is equal to KRO over mu OBO, just like we have for, okay. And then, so this basically goes like that. Here, above the bubble point, KRO is equal to 1. And then basically what they give a method to calculate the oil mobility as a function of pressure from either the bubble point, for example, here it's more or less a linear function, or something like that. And then if you, so this would be for a situation for reservoir pressure being greater than the bubble point. When you reach the bubble point, the average reservoir pressure reaches the bubble point. So let me draw that as green here. So when reservoir pressure drops below the bubble point, then what happens is this endpoint for the saturated region, this will drop here as the average reservoir pressure drops. So drop like that, like that, like that. So as the reservoir pressure drops, and then you'll get something that kind of goes like that, goes like that, like that. And they give a method for finding these lines, this oil mobility when you're in the two-phase region. Now, the values here at the average reservoir pressure as it depletes below the bubble point, this comes from the solution gas drive material balance, okay? So the solution gas drive material balance, that's, I don't know who was the first one to really, Muscat probably came up with it, but in a differential form. You've maybe heard of the Turner. It's a method to, there are many, many people who have addressed this, but this solution gas drive material balance basically says that it gives you as the average reservoir pressure starting at the bubble point, because this is solution gas drive when you start getting that, and then as you go down here, it gives you a means to compute the amount of oil recovery, kind of the average oil saturation at the average reservoir pressure. It gives you the ratio of KRG to KRO at the average reservoir pressure. And that allows you to get the producing gas oil ratio at the average reservoir, basically the producing gas oil ratio, okay? So if you've ever done imbalance material gas solution gas drive material balance, these are the numbers that you get from this analysis. And once you know the KRG KRO, you can also get the KRG, or I'm sorry, the KRO at average reservoir pressure. Okay, and this is this is what you use to get these green dots here. So basically you calculate first that, and then you get KRO over mu BO at the average reservoir pressure from that. And those are the green dots here above. So this is all the results of any solution gas drive material balance for reservoir pressure less than or equal to the bubble. Okay? And if average reservoir pressure is greater than the bubble point, greater than or equal to the bubble point, then basically you just have a very simple material balance with, basically BOI and BOB, BO at the average reservoir pressure, controls the recovery plus compressibility. And the producing gas oil ratio is just the initial, even though the bottom hole flowing pressure may be less than the bubble point. So you assume that there's no alteration of the producing gas oil ratio, even though the flowing bottom hole pressure goes below the bubble point. So this is standard reservoir engineering 101 for oil reservoirs. So you basically got a single phase. This is your material balance for that, and then for regardless of flowing bottom hole pressure being greater than or less than the bubble point, this is always both assumed and shown by reservoir modeling. Back in the 1960s, when they got reservoir simulation models, they did simulations and they showed that you basically got very little reduction in the producing GOR when the flowing bottom hole pressure went below the bubble point. So this is so the material balance gives this point here, but then this paper in 1941, Evinger-Muscat gave these lines. Okay, so the Evinger-Muscat basically gave a method to come up with the oil mobility between PWF and P average, which was less than or equal to the bubble point. Okay, so these lines here, this line, these lines down here. Whereas the symbols here, the endpoints at the average pressure, they came from the material balance. And they're not straight lines, they're functions, but they look more or less as a straight line. And so when they did this paper, what they made a certain assumption that they didn't know how good or bad the assumption was. So the Evinger-Muscat 1941 paper made the assumption, which was luckily a good one. They didn't have any way to prove it. Okay, is that basically that the flowing composition or the flowing gas oil ratio was constant throughout the entire reservoir. Entire drainage volume from RW out to RE. Okay. So when the average reservoir pressure was greater than the bubble point, that producing GOR was equal to RSI, the initial solution gas oil ratio. And when the reservoir pressure was less than the bubble point, the producing oil gas ratio was from the solution gas drive material balance. And so that was the first thing. And the second thing is that what that implies is that the entire reservoir is this as a steady state flow region um, 1 and 3. That's where the reservoir pressure at some radius is less than the bubble point, and this is where the pressure at a given radius is greater than or equal to the bubble point. In other words, single phase oil, so there was no region 2. Okay? No region 2. So the flowing composition, the flowing GOR was constant throughout the reservoir for the entire drainage. And when you made that assumption, then in the region 1, this Evinger and Muscat, they show that the ratio KRG to KRO could be computed. I think this is the equation, RP minus RS, which is a function of pressure, mu O BO, which is a function of pressure, over, I'm sorry, this should be G, over mu O BO, which is a function of pressure. And that gave the ratio KRG, KRO to be a function of pressure. So in this region 1, we have that pressure is less than the bubble point. We know the producing at a given point in time, we know the average reservoir pressure, we know the average producing gas oil ratio. These are from our material balance. Okay, so that's a given. And these are all just PVT properties, right? pure PVT properties, which are a function of pressure. So, but what we need what we need to get the rate equation, to get the lambda, what we need to get this to find, the rate, the oil rate, we need the mobility as a function of pressure. And so if you had a set of rock relative permeabilities, then you would have like oil saturation, KRO, and KRG. Okay? That would be your rock relative permeability, right? But what we knew over here is a function of pressure. We knew the ratio KRG over KRO. We knew that as a function of pressure. And all we need is KRO, in the mobility of oil. So how do we get this? Well, if I gave you a table of oil saturation, KRO, and KRG, and I said the ratio KGKO is 1, okay? How would you go get the KRO? Okay. Well, the best way to do that is you make a new column, which is the ratio here, together with the other. And in a certain block of saturations where both KRG and KRO have non-zero values, you've got these values here, right? So what you do is that at this pressure here, let's say this is the bubble point pressure, 4,000, you go to 3,500, and you calculate at 3,500, this is equal to 0.03, the ratio. So you go into this 0.03 here, and you find 0.03, and you go across here, and you get your KRO, okay? All right. So we transform, and they actually show figures. They don't show figures of saturation relative permeability. They actually show figures giving KRO as a function of KRG KRO ratio. And it starts for oil reservoirs, it starts down here, and this curve looks something like this, and they put it on a log scale. So this is 0.001, that's 1, and that's maybe 100. So for the 0.003, they go in 0.003 or 0.03 there, we got that, and then we get this value of KRO.
So if you plot KRO versus KRG over KRO, it's always monotonic. That's why
it's always monotonic, and it starts up here close to 1 and goes down towards 0.
That's why you can get this value from the table. Otherwise, you can have, if it's not a monotonic function, then you can have two values of KRO with the same ratio.
No, it'll always be monotonic, guaranteed. Yeah. So you go in at a given pressure, you have the KGKO, you go over and get the KRO. And I don't want to be lying, so I have to go find one of these figures. Here it is. Okay. This is KRO on the y-axis, and this is on the x-axis is KRG over KRO. That's RP minus RS. It's the same thing I wrote. It's just okay, and it's not on a log scale, so it looks like this. If you put it on a linear scale, it looks like that. Put it on a log scale, it looks like this. Okay. So you basically can go down to 3,000. You can go all the way down to, low pressures you want, 15 psi. And of course, as you go to lower pressures, you get more gas coming out of solution. So down here, this might be at a 0.3 value. And the KRO is going to be, so here it might be 0.8, and here it might be 0.23. Okay? And that drives this down, not towards zero, but down kind of towards zero. So the shape of this is the fact that the lower the pressure, the higher the KGKO, the lower the KRO. So that's and then you can get your oil mobility from that. So they make this assumption that the entire reservoir is under steady state flow. Flowing composition is the same everywhere, be it single phase or two phase. And it ends up that this theory is actually a very good theory, very, very applicable. Okay. And they show this fundamental relationship for steady state flow. That also applies for gas condensates, but we'll come back to that. Okay. Okay, so that was 1941. It was only solution gas drive. And with gas condensates, nobody really paid it any attention because, from the 40s, 50s, and into the 60s, gas was kind of a nasty word, didn't have any value, 10 cents an MCF. And the condensate, you could more easily get oil than oil fields than condensate out of gas. It was more expensive. And so basically, gas condensate reservoirs really didn't come into interest in the industry until the 70s, 60s, late 60s and 70s. Okay, so in I think it was 67, 65, there was two papers, the one by Odell and Miller. That's the most well-known one, and a similar development by the U.S. Bureau of Mines, Eilertz, who did a lot of work on advanced gas condensate PVT. Wrote a book on gas condensate PVT. Had a massive amount of laboratory experimental work. They had a paper, but both these papers, what they did is that they applied the same assumption, steady state flow assumption, as Evinger and Muscat did throughout the reservoir, throughout the drainage void. Okay.
4 gas condensates.
4 gas condensates. Okay. And then it was probably used, I don't know how much, by who or whatever, but that was pretty much it until around 1973 when a guy at Amoco, Dale Fussell, I believe is his name, first name Dale Fussell. Maybe it was Fussell because both he and his wife worked for Amoco. I'm not sure if he was alone on the paper, but Amoco, which of course became BP in the, I don't know, whatever it was, 1990s or something. They had their main headquarters in Tulsa, research. He did a lot of fantastic technology. So this Dale Fussell used I think it was even a compositional EOS-based compositional reservoir simulator to look at, I think it was just a vertical unstimulated well, pretty sure. Could have been a fracture well because hydraulic fracturing started around the early 70s, so it could have been looking at that as well. But I think it was just a normal vertical unstimulated well. Okay. And what that paper showed, and they compared it versus the steady state flow theory of Muscat as applied by Odell and Miller and Eilertz. And what they found is that this, which should be the right answer, because this compositional reservoir simulator, this should be the right answer to condensate blockage, was much less severe than this steady state flow theory. Okay. So the Fussell work said blockage, condensate blockage, is much less important than predicted by this steady state flow theory, and you shouldn't use steady state flow theory.
When do you say what less important? What does it mean?
It was like the well, how should I put it? You know, maybe the well rate was 2, 3, 4, 5 times less than what the model said.
Oh, okay. So
2 or 3 times at least. So the steady state flow theory that was used by Odell Miller and Eilertz gave a lot more blockage effect than he saw in the simulator for the same data. Okay. But didn't really explain why. Okay. So this was the state of the industry.
But did he also look at this steady state flow theory for this solution gas trap, and it was okay for
that? Yeah, several other people did that.
Okay.
In the 60s. I think the papers there were a guy named Martin. There's Vogel. There was a bunch of people who did things that substantiated the steady state flow theory being valid throughout the reservoir for solution gas trap.